You do it enough. Memorize.
You guys see the screen?
But point, but you want. Yeah, I want to
Yeah.
understand it.
Okay.
He's good.
Okay, so we're gonna do repeat. One more question. So far, we've done one question on the exam. No, that's
Because they're only going to choose one.
one of all that stuff we went over. You'll get one of them.
Thanks, Bob.
Hopefully it's one without the math.
Okay. You might be lucky. All right. We're talking about time constants, phase relationships, phase angle and reactive circuits, and admittance and susceptance. One of my favorites. I'm not sure I've ever used it except on the test.
Accept on the top.
What?
Says acceptance and then you say accept. on the
Oh.
top, so it's confusing.
When you put a voltage on a series circuit, okay, you charge the capacitor up, and how fast that capacitor charges depends on the series resistance. In other words, the RC values in the network. And that RC is what we call the product of those, is what we call a time constant. It turns out that after 3 time constants, you're effectively charged up or you're effectively discharged. Okay, so 1 time constant is the product of resistance times capacitance. And it charges up 63.2%, or it discharges 36.8%. You can see on a graph coming up where there's draws. 2 time constants, it's up to 86.5. In 3 time constants, it's up to 95. So it's essentially, and we approximate 3 time constants is what it takes to charge up a capacitor or inductor. Normally, we do it with RC networks. Here shows the charge and discharge paths, and they're crossing there at 50%. So 3 time constants gets you can see there it's up at 95 on the chart, or down 5 with the discharge. You don't have to use that formula on the exam. E to the 1 minus epsilon minus T over tau power. I had to use it in school though. What is the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the applied voltage, or to discharge to 36.8 of its initial voltage?
B.
Bravo.
B is correct.
Very good. What's the time constant of a circuit having 2 220 microfarad capacitors and 2 1 mega ohm resistors all in parallel? Get out your calculator. I think you want to see if you remember how to do parallel capacitors and resistors in this one also.
Well, that's easy. You do that in your head with that, but is this looking for the time constant formula? I'm saying delta.
I'm gonna say D, yeah.
So the answer is B.
I'm thinking B.
Oh, the resistors are in parallel. Okay, so 440 by.
Yeah, you got a half a mega
Oh,
ohm,
oh, yeah, you're right. So the answer is
240 microfarads.
so the answer is D.
But it turns out the same as 1 times 220. It's half times 440.
Yeah.
So it's just a little exponent exercise. Okay, if we only have resistors in an AC circuit. The voltage and current are always going to be in phase, because resistors do not have any reactance if they're real resistors. If it's a wire wound resistor, then this isn't true, because they have inductance. But we're not talking about that.
But carbon is evil, so we're not getting with it.
Oh, okay. Do they make them out of anything other than carbon type material?
Not in this.
Carbon film?
Yeah,
Although, well, that's true, not true. And diodes look like a variable resistor and they're not carbon. So the current increases when the voltage increases and it decreases, so it's proportional, it's straight Ohm's law. If we have capacitors or inductors, then we have to take phase into account. So when you apply an AC voltage on the capacitor, we say that the current leads the voltage by 90 degrees. And there's a saying to help you remember this called Eli the Iceman, which means for E, okay, for an inductor, okay, leads I. So the voltage in an inductor leads the current. The current in a capacitor leads the voltage. So it's a real easy way to remember those formulas. So Eli the Iceman. They never taught me that in school.
I go in that.
Did you?
Yeah. High school electronics, high school work, didn't have nothing. So you're. It can get confusing because. That's what you get for attending an Ivy League university and wanting to some.
Yeah, right.
Simple stuff. We got the calculus version of it. No, because they'll say, like the current lags the voltage, and what is what.
Yeah.
So both leads the current, or the current lags the voltage.
And they do bring up a question where they switch it.
Yeah, so
So
you can't remember leading and lagging, but you got both conditions on the country and the faster, so.
okay, so if we have capacity phase shift, okay, we can see that the current is leading the voltage from a phase standpoint. It's a negative phase shift. What is the relationship between AC current through a capacitor and the voltage across a capacitor?
Cal. So we're talking about capacitor, we're talking about the ice spring. So picture ice, where is the I and E?
I think it's A.
Currently it's about infinity, right?
It's AC, right?
You saying Charlie?
No, I said A.
We're doing
Delta.
Eli
Delta.
ice,
Delta.
man.
How many deltas we got? Delta's got it. The Iceman.
So that's the way to remember again, so capacitor, ice, where's the I and E? So inductor, it's Eli's, where's the E and the? Have you learned at MIT or Harvard? Let's get it.
Okay. The relationship between a current through an inductor and the voltage across it is just the opposite. Just virtually everything between capacitance and inductance is the opposite of the reciprocal. In the inductor, the voltage leads the current by 90 degrees. And we say Eli, in other words, the electromotive force in an inductor leads the current. This is the plot for just a simple inductor. You can see the current has a positive phase shift. So its current is lagging the voltage, or the voltage is leading the current. What's the relationship between the AC current through an inductor and the voltage across the inductor? Alpha. Eli. Now we have a series RLC circuit. We've got a resistor, capacitive reactance, and inductive reactance. So the impedance is going to be R plus JX minus JXC, the inductive and capacitive reactances. And they're opposite polarities on the complex plane. So we plot resistance versus reactance. And reactances are imaginary, which is why we use J, which is, if everybody knows, the square root of minus 1. So passive reactance will be negative, so it's on the bottom half of the complex plane. Inductive reactance we plot on the top half. And we represent the impedance as a vector, R plus J, whatever the resultant reactance is. So let's see. And once again, they're saying reactance is inductive, the voltage leads the current, the phase angle will be positive. If it's capacitive, the voltage is lagging and the phase angle will be negative. We're getting ready to talk about polar plots. And instead of just representing on rectangular coordinates vector for polar stuff, we can also represent it as the magnitude or the length of the impedance part of this triangle and this phase angle. So if it's inductive, we've got a positive phase angle, it will be on the positive upper right quadrant. If it's capacitive, it's going to be negative, so it'll be on the bottom right quadrant of the graph. And the magnitude is Pythagorean's theorem, the square root of the squares of the two sides. So it'd be the square of the resistance and the square of the reactance. Take the square root of it, it gives you the length of that vector. And if you want to do, this is another calculator one, which will come up. To find the phase angle, if you know the resistance and reactance, then you take the arctangent of the ratio of those two. So what is the phase angle between the voltage across and the current through the series RLC circuit if the capacitive reactance is 500 ohms, resistance is 1 kilo ohm, inductive reactance is 215 ohms. So first you have to figure out what the effective reactance is.
Is that the answer in the over? So look at capacitive reactance is 500, inductive reactance is 250 ohms, so the net circuit is passive. Right?
And what's the sign?
The sign would be negative.
Right. So we have 1 kilo ohm and minus 250 ohms reactance. So we have a ratio of
Well, I look at since it's net capacitor. Remember Eli Weissman. So the capacitor current leads the voltage, you can eliminate 2, answer right off the bat. Right. So
and
voltage.
you need your calculator to do the degrees.
Yeah, the actual degree, but right off the bat, if it's a net, this capacitive reactance, this capacitive reactance higher. It's ice, it's a current lagging, voltage lagging. Voltage is lagging current, right? So it's either C or D, you get that far. And if you've gotten that many answers correct and you want to do the math, just get your quarter out and move on to the
Beyond that,
next question.
there's no way to. I can't do that in my.
Does everybody know how to do arctangents on their calculator?
I'm saying 68.2 degrees.
Only got 14.
I think it's more like 14
It's more like 14.
on my calculator.
No. Yeah, but you looked at the slides before.
Yeah, but I worked these out.
Yeah, I didn't work anything out.
Hey, Bob, how many math questions are gonna be on this lesson?
Actually, there aren't many more.
So being this is a full question, I would thinking about these question pool is how many times you can see a decimal zero versus a longer decimal. And just sort of see if any pattern emerges when you're studying the questions.
Yeah, there's those things you can pick up on by looking at the question.
Mr. Deductive reasoning over here.
Okay, how do you do arctangent? You do second and to the -1 power. And then you put in the ratio.
Okay.
So you put in -250 over 1,000. And then do a closing parentheses. Did you get 14?
Yeah.
Okay.
You're giving it away though, Bob, because you've got A up there by your question. Okay, I'll take that back.
Scratch that from the record.
Okay, what's the phase angle between the voltage across and current through the RC circuit? Capacitive reactance is 100, resistance is 100, and inductive reactance is 75. So we're going to have a -25 ohms reactance, 100 ohms resistance. So we got what, -25 over 100? Seems like that's the same ratio as -250 over 1,000, right? So the arctangent is going to be the same as the previous one.
You only have both questions on the test, it's both of them agree.
What's the phase angle between the voltage across and the current through? Capacitive reactance is 25, resistance is 100, inductive is 50. So this time we have a positive reactance.
All the ratios are the same, so it's positive reactance, which means.
The phase angle is
Leave it,
So it's D or
the
D.
ratios are the same, so it's still 14 degrees, so it's valid.
Oh, that 14.
All three question balls in here is 14 degrees.
Now, you're only going to get one of these out of group B.
Well. We're gonna get one of them.
Yeah, all these, there's only one on the test.
And then the whole 14 degrees.
So there's a good chance you get a 14 degree.
Just reading or writing.
Susceptance and admittance, basically the reciprocal of impedance and reactance. So the reciprocal of impedance is called admittance, or 1 over Z.
So what's the difference between conductance? Because one's.
Conductance is the reciprocal of resistance.
Okay, so that's a straight with notation.
Right.
Once you start dealing with Z. And the reactances, then you use the term admittance.
It depends on the problem. Did somebody check in or check out,
Well,
or did I get email?
I must have got an email, 'cause you still got 4 participants.
Um, in some cases, it's easier to work with admittance.
Because they don't limit the term.
Well, if you're working with impedance, you know, if you do parallel stuff, you've got to do the reciprocal of the sum of the reciprocals. If you're doing the same problems in admittance, then you add them. You don't have to, for parallel, you don't have to do the reciprocals. So the math is easier for some things, depending on what you're doing. In here, they just really want you to know the terms. There, I don't recall any actual problems. Even when we do the Smith chart, where it's one of the places where you would use admittance. If you are familiar with the Smith chart, the reactance curves and resistance circles, there's also on a lot of them a separate set of admittance and conductance, susceptance curves, just on the opposite, starting at the 0 point.
But I
And
don't
it makes
think,
it easier to do a matching network because you can go from one to the other, the conjugate match.
I don't think anyone here's gonna admit to anything, so, you know, this conversation is dead.
So admittance is the inverse of impedance. Susceptance is the inverse of reactance. That's the imaginary part of the admittance formula. And we use B to represent susceptance. We use Y to represent admittance. And there, don't do it here, but we use what is conductance? G for conductance. No Y equals G. So the reciprocal resistance is conductance G, and it's in Siemens. It wasn't all that long ago, these all used to be in Mohs, which was ohms spelled backwards. And for some reason, they decided to give the Siemens guy credit. I don't know why that happened. But it's probably on Kathy Love's physics. The reciprocal of reactance is susceptance, and we use a B. The reciprocal of impedance is admittance, and we use Y. And this shows the standard impedance equation for the vector representation, which is resistance plus the imaginary reactance. Or in the polar form, it's the magnitude of Z, or the vector length, at the phasing. Likewise, admittance is the conductance plus the imaginary susceptance, and it's polar wise, it's the reciprocal of the impedance vector at a negative phasing. So if you have impedance and they want you, the question is to convert it to admittance. Remember, you have to take the reciprocal of it and change the sign. Did I go backwards? Yes.
Yeah.
So what is admittance?
Hey.
Okay. It's the inverse of impedance, 1 over Z. How is impedance in polar form converted to an equivalent admittance?
You say you have to change the sign. Well,
And you do the reciprocal magnitude and change the sign. B. What is susceptance?
So
C.
Imaginary part of it. So to try to remember those, impedance impedes the flow of current. So the reciprocal of that is admittance, it admits the flow of current. And resistance resists, conductance, which is the reciprocal of it, inducts. So the terms kind of make sense if you really think about it. What letter is commonly used to represent susceptance? Called.
Yeah. I'm not taking the exam, so. We can guess.
You're just here to power down.
That's right.
What happens? What happens to the magnitude of a pure reactance when it's converted to a susceptance?
That's a reciprocal, yeah.
Reciprocal.
Key there is. In the question, magnitude. So you're not talking about phase anymore. Or whatever, the sign,
Right.
just magnitude. And the
The
magnitude.
length of the vector.
Yeah.
Oh, that was a quick one.
But that means we'll get one of those.
One of those will be on the test. So if you're lucky, you get the easy one. Like what letter do we use to represent?
That's memorization there.
Yeah,
And there's 50 questions in this test?
there's 50 questions.